Thank you, Senator Cruz. Now, please welcome Rodolfo Rosini, co-founder and CEO of Vaire Computing, for a tech talk.
Thanks, everyone. It's going to be less of a tech talk and more about, I want to share my perspective so I understand why I'm doing what I'm doing, right? And why this is important. So the font gets bigger as the presentation progresses. Don't worry about it. So I founded this company 4 years ago, and there is barely anything public about it. We basically realized that there was an opportunity in the market. Nobody was working on this thing called reversible computing, and decided to give it a shot. My background was, as I mentioned before, was an entrepreneur in cybersecurity and AI. If you're in DC and you call Verizon and you're concerned about Salt Typhoon and you want to make a secure phone call, you get to use the software I wrote in my kitchen, so 20 years ago. My co-founder, Hannah, is world expert over reversible computing, and our co-founder, Andrew, is the founder of a British company called ARM. If you take all the world chips, except the one designed by ARM, and you put them together, they're still fewer than the one ARM designed. So they're pretty big. We originated in the UK, and we're still based in London and Cambridge, and in the Bay Area in Seattle. But majority of our employees are in the US at this point, and we're creating more jobs here. So, I'm sure by now you've heard about the fact that AI uses a lot of energy, so I really don't want to talk too much about that part, right? But I want to give you a couple of data points, right? The first one is that because computing really grows exponentially, right? And so you can start building 10 data centers with 10 nuclear power stations, and then you build 100 nuclear power stations, and then you need to grow more, right? The fundamental problem here is the conversion of energy to information, right? So chips are catastrophically bad about this conversion. And by catastrophically bad, I mean less than 0.1% of the energy in a chip is actually converted into information. Everything else is wasted as heat. And even if we were to build infinite nuclear power station, which is not a given, you still run out of water, because what we do, we build this chip, they get super hot, they do computation, and then we have to cool them down, right? So we basically paid the penalty twice. So the problem is also from an industry perspective. This is the chart that's not been updated in the last few months. It's for the previous 2 years, which is about majority of the funding went into things that are not chips, right? Went into infrastructure and data centers and AI models and everything, right? And really the part that mattered, the computational layer, which is at the bottom, really had very, very little funding for reason we explored in the previous panel. And so what are the options that we have, right? And so, and by the way, this is CEO math, so don't really follow it. Just to give you a sense of the orders of magnitude of the problem, right? So right now, we're building more data center. That's sort of what the industry is doing, AWS, Azure, and so forth. Half of the world data centers are in the United States, and the rest a bit of in Europe and a lot in China, right? But really, we can't really grow in that way. It's expensive, it's predictable, but in previous panel, there is also a mention of the fact that when you talk about computer chips, there are really two types of chips, logic and memory. For historical reasons, they're very different in terms of materials, architecture, and the way memory and logic talk to each other is really inefficient, like everything, right? We simply made them faster and faster and faster, so there was never really a reason to really sweat the details, right? And now we're at the point where maybe we could do something with there, and there are some, orders of magnitude, one order of magnitude left, between 2 and 20x of efficiency left there. But really, the only thing that delivers a return long term is changing the logic substrate. And so what that does it mean, right? So this is, I would say, probably the most interesting slide that I'm going to show you today. This is how we see the world, right? And some people might not necessarily agree. So the part on the left is time, the bottom is digital, the top is stochastic. What I mean by this is that the yellow stuff is what is today accepted, what's happening in in the major labs, which is essentially increasing and like I say, non-disruptive innovation, right? Continuous innovation, basically you do some more engineering, you make it like slightly more and more efficient, right? And all these things are great, but as Dr. Mason this morning mentioned, we are like one or two generations away from basically not having the ability to build faster computers, right? And the stuff that is green and blue on the right is basically everything that's coming, right? Or at least some of the most promising architecture that are happening. And the two big differences here is the one at the bottom, right, which is digital logic. So when we think of bits and 0 and 1, and statistical, probabilistic, stochastic, there are multiple names, where basically 0 and 1 are not quite that different. So think of probabilistic computing, where there throws a lot of errors, but it's so cheap from a computational perspective that you can still get good results, or quantum computing, which is probably the most pure expression of this, right? The problem is that, and I beg policymakers, right, to really think in these terms, to stop thinking in these terms, that the situation is not that you have classical today, which is digital, right, what we call binary, and tomorrow you're going to have quantum computers. Like, absolutely not the case, right? Everything that's in the top right corner, first of all, is decades away. In some cases, it might not ever be viable, right? So it's something that, quantum computers, we might not be able to see in our lifetime in some cases, or at least not as general purpose computers, right? They're all things that are additive. The only thing that matters is the part in the bottom right. And so to give you a sense of like where things are, so analog computing in the top left is probably worth today $80 billion. Quantum computer today in revenues is probably $1.4 billion. And the bottom right is on aggregate $3 trillion, growing to $5 trillion by the end of the decade, right? So really, like, everything else is a rounding error. And the most important thing we can do is continue our existing architecture, right? For maybe people of my age or older, you might have heard of COBOL or Fortran, invented in 57 and 59. We still have these systems in production, right? And so thinking about believing that you can completely throw away that infrastructure and change and move to statistical is simply not true. It's not going to happen. We're going to stay with binary for a very long time. So extending that is the most important stuff. So what am I doing, right? You might have heard of reversible computing, but reversible computing is a very, very wide range. We are working, and we invented something called near-zero energy computing. There's very little to next to nothing publicly. Over the next 2 months, you'll hear more about it as we will unveil our chip. And essentially is the idea of having a chip that uses almost no energy, that is the most efficient way of converting energy into information, with a secondary added benefit that it's a chip that doesn't get hot. So it releases almost no energy, right? And you can still run it like super hot if you want for extreme performance, but the idea that you don't have to. And if there's someone with a background in electrical engineering, this is I can say, a variant of what would be called a reversible adiabatic computing, but because it's a bit of a mouthful. But think of it as a regenerative braking in cars, right? So you perform an operation, and when you have extra energy, you just recover it. That's roughly the concept that we're operating. It's not new. Von Neumann discovered it. He discovered it, thought about, he didn't write it down, and then he died. But luckily, he had spoken with a physicist from IBM who then wrote it down, and it's sort of, in 93, DARPA funded MIT to actually build the first prototype, and then really nothing happens. The most important thing is that not only this does not require any change in manufacturing, but more importantly, it can deliver, we think, without changing the substrate, right? So with existing technology, a 4,000x increase, which is more than what we discussed that's needed, right, to get into the next generation of compute. So we think our chip is going to be 3x. We're a company of 20 people, so it's we can't really, 3x compared to what, say, NVIDIA or Intel are doing today. But of course, it's not apple to apples, right? So our product will arrive probably in a couple of years. So we're not going to have a 3x increase over their product, right? But if you think a company of 20 people building something that can match the performances of a company that's worth more than 30 trillion, I believe, today, it's sort of like a good place to be, right? We think that these will be transformative in 3 domains, particularly. So one is in the autonomous fleet, of giving the smallest drone the big possible networks, right? And so having large vision model or language models on drones in advanced computing space, and of course, data centers. The idea that you have a fixed power envelope in a data center, you need to build infrastructure, and we can convert the existing energy going to the data center in much more compute and much more efficiently, and reduce the cooling and the use of water for this. So again, this is, previously was CEO math, this is CEO hallucination, but the idea that the CPU from Intel, like dominated 30, 40 years, right, of the world. And now we're in this era of 20, 30 years where the GPUs from NVIDIA really dominate the market. We believe that our architecture, or at least a reversible architecture, doesn't necessarily have to be us, will dominate the next 15 to 20 years, right? We think this is inevitable. This is absolutely a hugely controversial statement that I'm saying here. I guess time will tell, right? But I bet my career and my credibility on this, and I think I'm right. So the reason why this matters is because we don't have a choice, right? There is no third generation. There is nothing, right? And really, like, even if analog and quantum, they become a $100 billion company, $100 billion market, it doesn't matter because classical is 5 trillion. And really the value is that the additional thing is that China is primarily an agrarian early industrial society. So if we reach the end of Moore's law, we can no longer grow our economies. For the West, this is a disaster. For China, they can actually grow for decades before it can digitize and really reach the end for them. So it's really worse. So I keep talking about this in the future, but actually, we already done it. So we have proved that this works. We have done our first chip. It was entirely funded by private money. We're based in the UK and the US, but we received 0 taxpayer funding, R&D, or anything from either government. And we're planning to build this product and ship it to hyperscalers in 2027. We're probably under NDA with half of the room. And if you don't know about this, we'd love to talk to you for the other half of the room. So very much come and talk to me, and thank you very much.
Our next panel explores how the United States